Welcome back, everyone. We're taking the problems from this book. The book has problems and solutions. I've transcribed both the problem and solution here, and we will be turning the informal versions into formal Lean 3 code. Let x, y, and z be integers with z greater than 1. We want to show that x plus 1 squared plus x plus 2 squared plus and so on, x plus 99 squared is not equal to y to the z. So the way we translate that into Lean code is like this here. A few things are going on here. One is I made z a natural number rather than an int. If I change that to int, I get this error about failed to synthesize type class instance. We have this assumption that z is greater than 1, so if we can consider it to be a natural number. Our sum here we've written using the big sigma notation. That comes from this open locale big operators. I think it also needs this big operators pi import. There's an off by 1 thing happening here. In the informal version it's x plus 1 dot 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 x plus 99, and here it's each of the terms is x plus I plus 1. When we go over this range, I will be 0 indexed, so we'll start at 0 and go up to 98. So at 0 we're at x plus 1, which corresponds to the first term, and then at the end we're at I equals 98, which corresponds to x plus 98 plus 1, which corresponds to this term. So let's get started. First thing is just to take that not equals and take it over to the left. Not equals is syntactic sugar for the equality implies false. Let's call it HE. We're assuming that the equality holds and we have to find a contradiction somehow. The only thing that's happening here is we are rearranging some terms, reassociating some stuff, factoring some stuff out. So here we have an arithmetic sequence that we have a closed form for. Then we have this sum of squares, which we also have a closed form for. So that's actually the part that I think is going to be most interesting about this. For this arithmetic sequence, I've made a note down here that in the math lib, there's a lemma that just has that fact. I don't know of a similar fact for the sum of squares, so I think we're going to have to prove that by ourselves, but it should be a simple induction. Once we have those closed forms, we see that there's exactly one instance of 3 in the prime factorization of y to the z. And since z is greater than 1, there must actually be multiple instances of 3 in prime factorization of y to the z, and that contradicts that there must be exactly 1. Let's just do it. Flipping HC sim, HE sim. So how do we write this? I in finset.range 99, I plus 1. Because we start at 1 and we go to 99. I will start at 0 and go to 98. Final term here is another sum, I plus 1 squared. Probably we should split out a few more steps. So we want to apply a simple associativity thing here. This is a little bit tricky because it's underneath this binder. The usual way to do this would be to rewrite add sock. The problem is that rewrite does not know how to go underneath this binder. I might be able to do simp rewrite? No. I think I need to apply a congruence lemma. So I'm going to split this out. All I n x plus I. And indeed it is add a sock. Associativity of addition. What if I do rewrite add a sock? Good enough for me. I can do a little squared. Yeah. Finset sum conger. We're going to use this down here to rewrite under the sum binder. For maximum convenience, we're going to add an assumption here to h1 that we don't use. And then maybe just library search has what it needs now because I made that lemma. So we use h1 and sum conger. We're going to do a bunch of other things like that. Again, I need to import the ring tactic. Oh, I want to intro I, not x. I must be missing something. Oh, forgot how to multiply this out. I need an x here. Yep. As I did that, I realized that this first step, this h1 thing, will also be handled by ring. Just forget about that. And now we're going to break this thing up into 3 separate sums. First, this x squared one will turn into this term down here. Then this 2 times x plus 1 thing will turn into this term. And then this I plus 1 squared will turn into this final term. To remember the lemma that lets me do that, I can either go to the mathlib docs. I'm going to actually try that first. I'm just going to scroll down. I'm on the algebra big operators basic page. Sum add distrib. Yeah. This says that if we have a sum of f of x plus g of x, that's the same as the sum of f of x plus the sum of g of x. So we're going to apply this twice. Okay, broke off the first time. Now let's do the next one. Okay, when we had to use rewrite because it wasn't just like the top level thing, we had to descend into it a little bit. And now what I want to do is say that this equals 99 times x squared. I can pull the x squared out because it doesn't depend on I. Norm num, nice. Okay, now we want to do the middle terms here, so this should equal this. I think I wrote that wrong because the x went away. I need the x somewhere. The second term here has an x in it. Okay, let's first pull out the 2 times x, 2 times... There should be a lemma in mathlib that lets me just take this 2 times x to the outside of this. I'm just trying to find it in the docs over here. The problem is I need to import a new file here. I think that once I do this, library search should get it. Yep. Okay, I might as well roll these into a single line here. Now we've reached the time to use this finset sumRange ID. That lives in algebra big operators intervals. Doesn't quite match what we have because we have I+1 rather than I in here. So the first step will be to change that. How do I rewrite that as something that just has I in here? It's going to have a different range. Can I just say norm them? No. Both of these should be adding up 1 plus 2 plus ... plus 99. The second one technically has more terms, but the first term is just 0, so they end up lining up. I want this thing called finset sumRange suck. My rewrite is applying to the wrong place. That does it, but it's super slow. Reset option, profiler. True. It's going to tell me how long each of these steps takes. 14 seconds. Why does nth rewrite take 14 seconds? Okay, that'll do it. So instead of using nth rewrite, which was taking ridiculously long, I just do regular rewrite, and then I indicate which term to apply to by specifying the implicit arguments by putting the @ sign here, and then saying I want it to apply to n equals 99. That corresponds to the second term. Oh, and I want it to be h4. Why doesn't that work? Because I have to coerce. Okay. And just collapse it down. And now I think I can apply sumRange ID. 100 times finset dot sumRange ID. Why not? SumRange ID is only talking about natural numbers, and down here we are in the integers, so we're going to have to do some sort of norm cast thing. Pull it into its own lemma. I'm worried that using this subtraction is going to be annoying, actually, because subtraction on natural numbers is awkward. Oh, it's like more annoying than you would think because integer division is annoying. So maybe I do this when I use the existing lemma. Ha! Okay, just needed some finessing of the casting. I think I can roll this into what I did before. And now we have arrived at the sum of squares formula. It would be cool if I could just use an existing lemma, but I don't think there is one. I don't actually know it off the top of my head. And I think I'm actually off by 1 here. I want to do I+1. And this has the advantage of I+1. It's closer to what we already have down here to match. Yeah, and then so here the tricky part is just going to be dealing with the integer division. I wonder how finset sumRange id deals with this. Oh, yeah, of course. First prove it with multiplication, then divide. The thing to prove first is this. Just want to know what the name of this distributivity lemma is. A plus b times c equals A times C, B times C. Addmul. So I can use addmul to distribute, and then I can apply the notion about this, and then maybe just ring. Come on. Really? Ring wasn't working because of the successor and dot suck. Okay. So I just copied the idea from the sumRange ID proof. I just copied the code from it actually, and it just worked. And we'll do a similar thing that we did for the sum of 1 plus 2 plus ... plus 99. Except in this case we have squared. At least what our informal proof says is that it's this. And again, the problem is this casting in between nats, ints. Norm num is telling us that this does in fact not equal this. I was off by 1. I think I can apply this then. Nice. And we'll roll this back into that previous step like we've been doing. Now we just need to pull out the 33. Gives me this really scary looking error. Deep recursion was detected at expression equality test. Potential solution, increased stack space in your system. Probably just Ring is not happy with numbers this large. Wonder if I need to do like norm num first. There you go. Great. That's the calculation part. Now we just need to do the divisibility part. So 3 divides y to the z. That should also imply that 3 divides y. Maybe this will be easier if I rule out the 0 in the one case. If z is 0, that contradicts this contradiction here. 1 is less than 0. I can write y to the z dot suck as y times z dot suck. Actually, at this point, I don't even need to do it the second time. Maybe that does not actually help me. If 3 divides y to the z, where z is at least 1, then 3 must divide y. So I was just trying here to distill this fact we want to use down there. We have 2 numbers, 2 natural numbers, a and e. E is greater than 0. And 3 divides e to the e, then 3 must divide a. Do I have to say 3 is prime? Yeah, maybe I'm just missing importing some files that talk about prime numbers. Okay, yeah, here it is. Gotta import data nat prime. So how do I prove that 3 is prime? Well, there is a lemma called prime 3. Deck trivial would have been the tactic. I didn't even need this HE part. Right. This whole int nat thing is so annoying. Okay. Oh, I think now I want to do the cases thing. This should be enough for us to get a contradiction now, because we have 2 factors of 3 on the left and only 1 factor of 3 on the right. This term cannot be divisible by 3. That's the whole point. This piece is divisible by 3, this piece is divisible by 3, but this piece is not. Okay, this is so close. We have h12, so on the left 3 times something, on the right also 3 times something, but plus 1. That's definitely a contradiction. I just need to get the remainder when I divide by 3 on both sides. There you go. Okay, done. Play the fireworks animation. Kapow, kapow, kapow. I went a long time there without saying anything. Let me just talk through what happened. We just wanted to derive a contradiction from this h7 thing. The left was divisible by 9, but the right is not divisible by 9. So first we peel off 1 factor of 3, then we're left with this h12, and now we want to prove that the left is divisible by 3 and the right is not divisible by 3. And so all this stuff down here was just about pulling this factor of 3 to the outside and then just having some easily dealt with remainder term. But after the rewrite, we have the 3 totally factored out here and also totally factored out here, and we have the plus 1 over here. And that lets us use the modulus operator and then norm num to get our contradiction. We did it. Thanks for watching.